Welcome to Topic 4, Atomic Structure and Electron Configuration. This is the first lesson, which is going to cover the historically significant breakthroughs in the field of chemistry in regards to the structure of an atom. I'm Mr. Rast, and for Halloween, I'm a Space Ranger. So first we're going to talk about some basic vocabulary on the structure of an atom. And hopefully before high school chemistry you've heard some of these things, but if not, these are the things I want you to know. First, that there is a nucleus. All atoms have a nucleus, and this is the center of an atom, which is made up of protons and neutrons. The protons are positively charged subatomic particles. Subatomic means smaller than or below. That would be the prefix below, and atomic would be atom. So this is a smaller than an atom, subatomic. So a positively charged subatomic particle in the nucleus of an atom, that's a proton. Key thing to note here is that protons are positively charged. The next important concept or term in an atom is, particularly in a nucleus, they're made up of protons and they're made up of neutrons. A neutron is a subatomic particle in the nucleus that is neutrally charged. So protons are positive, neutrons are neutral. It is worth noting, having taught chemistry for some years, that most students are fine with the definition of a proton. They don't seem to make a mistake on that. However, I have ran across people mistaking a neutron, and often students will, the common mistake is, instead of saying that a neutron is neutral, they'll say protons are positive and neutrons are negative. And I think it's because people are focusing on just the first letter, but I would infer that possibly you could refer, or I should say look at the first 5 letters. N-E-U-T-R is basically neutron, is pretty much saying spelling neutral. The third subatomic particle is electrons. Electrons are tiny negatively charged subatomic particles that are moving outside of the nucleus of the atom. So these guys are very small, they're moving around, they're not stationary, and they have negative charge. Okay. In the early 1800s, John Dalton presented some basic ideas about atoms that we still use today. He was the first to say that there are many different kinds of atoms, which he called elements. He said that these elements combine to form compounds, and that these compounds always contain the same ratio of elements. Water, H2O, for instance, always has 2 hydrogen atoms for every oxygen atom. He also said that atoms are never created or destroyed in chemical reactions. What laws was John Dalton talking about in this passage? Well, the first law is the law of definite proportions. The law of definite proportions is right here. It's stating that elements combine to form compounds, and that these compounds always contain the same ratio of elements. For instance, water is H2O. So the law of definite proportions is basically saying that water is always H2O. You can't make water in a different combination. For instance, H2O2 would be hydrogen peroxide. So if you had a ratio of H2O2, that's hydrogen peroxide. Water is only H2O. So that's a law of definite proportions, that compounds always contain the same ratio of elements. Dalton also came up with the law of conservation of mass. He said that atoms are never created or destroyed. So even though it might look like something burnt up and disappeared, those molecules are probably, when it burns up, are turning into a gas. So it might have been a solid that transformed into a gas and floated away. It was never destroyed. One thing I like to talk about with my class is that unless an asteroid hits or something like that, the atoms on Earth are the same atoms that have always been on Earth. They just changed forms. The atoms in your body have always been on Earth. They've been in different environments and making up different things. And so we're not creating atoms on Earth, and we're not destroying atoms on Earth. They're just changing states. I think of it, a lot of times I think about that is like Lego pieces, that they might be built up to make one thing, but then when you break them back down into pieces and rearrange them, um, that's what's happening in chemistry, so all the time. So the pieces, we're not getting new pieces or losing pieces. They're just being rearranged in different forms. In 1869, Dmitri Mendeleev and Lothar Meyer independently proposed arranging the elements into early versions of the periodic table, based on the trends known as elements. We'll get into this a lot more in the next, in the fifth topic. This is the fourth topic. In the fifth topic, I'm going to go deep into the periodic table. But for this topic here, all I really want you to know is that Dmitri Mendeleev and Lothar Meyer are the first people to rearrange the elements in a periodic table. This is a picture of a modern periodic table. They didn't make this. They had some mistakes in theirs, but it was relatively very good idea. If you notice a periodic table, it goes 1, 2, 3, 4, 5, 6, 7. It's going in order. But why not just list it in order like a book? You know, just write, and then when you get to the end of the page, just start the next one. They rearranged it so things in the same column have properties like each other. Now, they're definitely different elements, but they have similar properties. For instance, if we look at this column right here, this column here is helium, neon, argon, krypton, xenon, radon. These elements here are all gases, and they're all very non-reactive. They don't like to react with other things. Where just one element away, this is number 10. If you go to number 11, sodium is a silver metal that's extremely reactive. It reacts with everything. In fact, if you put it with water, it will react violently with water and produce a little flame as it bursts. It'll split the water molecules into hydrogen and oxygen, and it's so hot it'll ignite it. So very different between element 11 and element 10. But element 11 is a lot like everything in this column. These lithium, sodium, potassium, rubidium, cesium, francium, these are all metals that are very, very reactive. So that's what these columns have things alike. So what they did is they just took it in order of mass. Back then they did it by mass. And then they set them up in columns based on the trends. And they found it interesting that these patterns kind of would repeat in order. So it would go a metal, and you might have a gas that's very hazardous, a very reactive gas, and then to a gas that's very non-reactive, and then back to a metal that's very reactive. So we'll get into this in much more detail, but that's basically what I mean by them proposing a periodic table, laying it out. All right, so at this point here, we've got some periodic tables laid out. Dalton proposed that there's elements. He's the first person to say that they're elements, and then we have Mendeleev and Meyer setting up periodic tables. In the late 1800s, J.J. Thomson watched the deflection of charges in a cathode ray tube and put forth the idea that atoms are composed of positive and negative charges. The negative charges were called electrons, and Thomson guessed that they were sprinkled through the positively charged atom like chocolate chips sprinkled through a blob of cookie dough. So J.J. Thomson, what's really important about J.J. Thomson is that he's the first person to say that, you know, atoms have more to it. It's not just an element, but they have charges, and these different charges he named electrons. I like to give the example of chocolate chip cookie dough because the example that from what I read that he actually gave, so I kind of added this cookie dough idea. He uses plum pudding, which one, I don't know what plum pudding is, and two, I don't think I want to know what plum pudding is. I really don't like the consistency of pudding. It's kind of gross to me. It's slimy, and I just would much rather have a picture of a chocolate chip cookie on here. I think plum pudding is some kind of pudding with raisins in it, and the raisins would be the electrons. I don't know, and I really don't want to know. All right. So the next important breakthrough here in chemistry is that Robert Millikan was able to calculate the charge of an electron by examining the behavior of charged oil droplets in an electric field. What I would take away from here is J.J. Thomson proposes or comes up with the idea that that a atom has electrons, and Millikan figures out, he calculates the actual charge of an electron. So now that we know that there are electrons, we're doing experiments to test and understand these electrons, and so Millikan actually figures out the charge of the electrons. So he's going one step further. All of these ideas keep building on each other. You're not going to be needing, on the test that I write, I'm not going to ask you about dates, but I will expect that you understand the sequence and who added what to the field of chemistry and what did they add and what was there before, what was, kind of situation like that. So you should understand Millikan comes after Thomson, and he elaborates, expands on the idea that of the charge of the electrons. Okay. The next breakthrough is from Ernest Rutherford. In the early 1900s, he fired alpha particles at gold foil and observed how they scattered. This experiment led him to conclude that all of the positive charge in an atom is concentrated in the center, and that the atom is mostly empty space. This led to the idea that atoms have a positively charged nucleus which contains most of the atom's mass, and thus the teeny negatively charged electrons travel around the nucleus. So what Rutherford did is basically, remember J.J. Thomson proposed that there's electrons in in a blob of something, like an atom is a structure with little negative charges speckled through it. If that was true, shooting alpha particles at these objects that, let's say that they're just kind of a blob with negative charge in there, the alpha particles wouldn't get through. They'd hit it and ricochet off. But what Rutherford found is that most of the time these particles could travel straight through. Most of the time the arrows, if you see in this diagram, make it straight through. Once in a while they get deflected. Sometimes they get deflected straight back. So this changed the model, changed the idea that J.J. Thomson proposed into this more current view of the structure of an atom. J.J. Thomson is still very important, important in the field of chemistry, because he's the first person to propose that there were electrons in the first place. Hey guys, I just took a little break there and changed into my dragon Halloween costume, so let's get back on the track here. So the next important step or lesson learned in chemistry was the breakthrough with the quantum theory. Max Planck figured out that electromagnetic energy is quantized. That is, for a given frequency of radiation or light, all possible energies are multiplied of a certain unit of energy called quantum. This is his formula. E equals, or the change in energy equals his constant, Planck's constant, times frequency. You're not going to do calculations with this for me on this thing, but what I need you to understand is that Max Planck figured out that the electrons are quantized. So basically, energy changes do not occur smoothly, but in small specific steps. That's what quantum means. So something to be quantized means that the change is not smooth, that it comes in steps. And so here's a little diagram of that. That the change would be in steps. In other words, you don't see a change in energy being linear, or I should say smooth, in that it could be any one of these things. It would be such as in steps. Let me try to illustrate this, because I know it's a bit of a confusing concept, but hopefully after this, hopefully after I explain this a little bit, it will seem pretty clear. So, let's see here. What he figured out was, let's see here. What he figured out was that if you've got the nucleus, you got the nucleus of an atom, and you've got the electron that's normally circling around, kind of an area like this. That's not a very good circle, but kind of circling around here. If you add energy to an atom, such as like adding energy to neon, what happens is that electron that's around here will jump up higher to a different level. It could be here or it could be another level here. So it'll jump up to a different level. And when it jumps up, say it jumps up to this level, when it falls back down, because energy is neither created nor destroyed, so as the energy gets added to the atom, um, the electron takes that energy and moves further away, but the nucleus being positively charged and the electron being negatively charged is drawn back to its original state. So as it falls back down, it took energy to rise, and then as it falls back down, it releases energy. And that energy will be in the form of a photon. And so photons have these wavelengths. So it will release a photon of energy. And if the wavelength happens to be in the visible spectrum, we see this light. So it could maybe fall from one stage, or it could have risen up here and then fallen back down over here. But what Planck found is that the electrons weren't just randomly coming up and down anywhere, that there was actually levels or there's actually levels that they're quantized, that would have to either rise and fall at certain levels. It's kind of like stairs. If you got some stairs, this pen doesn't always write for me. If we got stairs, a ball can exist on one level or another level, but the ball cannot exist at rest in between the stairs. So the electrons will find different levels that they'll come up and fall down to. And really, that's all that quantized means. Quantized just means that we're resting at levels. It's not a smooth situation. So some things that are quantized have levels. So let's take a look again, understanding that. So if this was the ground, this is the first level that the electrons could go to. They could rise to any of these different levels, and if it was here, it could only fall down to the very bottom, or it could fall down to this stage right here. So it could fall down here, or it could fall here. It can't fall everywhere. And because it has specific stages that it's falling, it's only releasing specific wavelengths. And that's why neon lights shine at a specific color versus a light that's made with helium. It'll be a different color also. If it didn't have quantized levels, when it fell down, because it could fall down at any level, it would give you all the wavelengths at once. Therefore, if you excited the atoms of elements, they would always give off a white light if they weren't quantized. The fact that they give off specific colors is because they are quantized. And we're going to do a really cool lab with this coming up. So remember the quantum theory when we talk about the colors that are released from excited electrons. That'll be coming up. Okay, so just to review, what does quantized means? What does quantized mean? Electrons are quantized. This means that electrons can only exist at specific energy levels. The positively charged nucleus is always pulling at the negatively charged electrons. The further away the electron is from the nucleus, the more potent the more potential energy it has. So the further away, the more energy it has as it comes back. So my note here is that that electron potential energy is like potential energy of an object held above the ground. However, electrons are quantized, so this would be like objects held above the ground on stairs. The object could never be held in between the stairs. So if you think about what quantized means, is it just means that there's steps. There's certain steps that you have to exist on. You can't exist just anywhere. All right. If we take the idea that Rutherford came up with, and that was that there is a nucleus, and then that it's mostly empty space, and that's where the electrons exist, and then we also combine that with Niels, not Niels, but that's Niels Bohr that we're talking about now. But if we also talk about this with Max Planck's idea that they're quantized, so if we take Rutherford and Planck's ideas together, we come up with the Bohr model. The Bohr model is basically that here it's just a model of an atom, which would be mostly empty space with a small nucleus in the center, and showing that electrons are quantized, that they have different areas that they exist at. So Niels Bohr took the quantum theory and used it to predict that electrons orbit the nucleus at specific fixed radii, like planets orbiting the sun. The Bohr model worked for atoms and ions with one electron, but not for more complex atoms. So it's a very simplistic model, and it does have some flaws with it, and it really only works if you're talking about one electron. So these rings don't actually work very well, and we're going to get into electron configurations in a couple lessons, so we'll talk more about what the actual structure is. But you can understand where the Bohr model comes from. If you take Rutherford's idea and you take Planck's idea, the Bohr model makes a lot of sense. But the reality is that we can't really figure out exactly where an electron is at any given point in time. So Warren Heisenberg said that it is impossible to know both the position and momentum of an electron at a particular instant. In terms of atomic structure, this means that electron orbitals do not represent specific orbitals like those of planets. Instead, an electron orbital is the probability function describing the possibility of that an electron will be found in a region of space. Heisenberg's uncertainty principle states that you can't really say that an electron is orbiting around. I mean, we can predict where Earth is going to be in a year from now, 2 years from now, minutes from now, because it has this predictable pattern as it goes around the sun. Electrons don't. That's what Heisenberg is saying. So it's not this that they're just perfectly moving around at a perfect rate, that it's impossible to note the position and the momentum at any particular instant. So instead you get this area of probability, and if you notice that it's darker in the center of these areas of probability and lighter at the edges, that would tell you that the probability of an electron would be found in these regions here, more likely in this area and less likely out here, but certainly more likely in these areas here than out about and around in here. So it's just an area of probability is what Heisenberg is talking about. By the way, little pop culture note, Heisenberg is the name, if you've seen the show or heard of the show Breaking Bad, the chemistry teacher used an alias name in that show, and the name he used was Heisenberg. So that would represent that he is a bit unpredictable. It's uncertain. So, and I think he was rather unpredictable and uncertain of what he's going to do next in that show if you ever watch it. Okay. All right. The de Broglie hypothesis. Louis de Broglie said that all matter has wave characteristics. This is important because sometimes the behavior of electrons is better described in terms of waves than particles. There is a simple relationship between an electron's wave and the particle characteristics. So the upside down y is a lambda, and lambda represents the wavelength associated with a particle. As the denominator, m would be for the mass of the particle, and the v would be the speed of the particle, or velocity. That's why it's a v. If you multiply mass times velocity, you get momentum, which would be a p. So basically what you're saying here is your denominator is momentum. H is the Planck constant. So Planck's constant, remember him, he talked about things being quantized, or electrons being quantized. So our formula here is the wavelength equals Planck's constant divided by the momentum. So if we take the mass and velocity of something, divide Planck's constant by that, we can get a wavelength. The reason I bring this up, the reason I want you guys to understand this, is that we don't study electrons directly. We study the wavelengths they release. We study them indirectly because they're just moving too fast. They're too small for us to actually hold down and study the electrons. So we're using the de Broglie hypothesis to study the electrons indirectly. So I'd like you to note that the de Broglie hypothesis is useful for very small particles such as electrons. For larger particles, the wavelength becomes too small to be of interest. So yeah, we could take our mass, a person's mass, and a person's velocity, but you'd have a very, very large number here. And if you've got a very large number, a very large momentum as your denominator, if you have a huge denominator, that will make your answer here very small. And so It works for anything, actually. It's just that our numbers get so small that it's not useful in calculations and whatnot. Okay, so that's the kind of the history of where we're at. So let's talk about how these things come together and our last little definition of what an atom is. So in my example here, we're talking about helium. Helium has 2 protons, 2 neutrons, and 2 electrons. So this is a diagram of helium, and we have our red dots are the 2 protons, our blue dots are the 2 neutrons, and we've got 2 electrons, but I really like this picture because it didn't draw 2 electrons. It's a picture with a cloud where these 2 electrons would have a probability of being seen. Out here, it's very light, and as you move here, it gets darker, so the probability would be more likely in this area, but it could be out here, and even closer to the nucleus. So that means that these 2 electrons are moving around this area at different rates, different speeds. You can't really know where it's going or where it's at any given point in time, but you have this area probability, and this ring here would be the most likely spot that you would see the helium atoms. Remember, this is 3-dimensional in real life, so this would be more of a sphere around this instead of just the actual just a circle. So anyways, good picture. So a proton has a charge of +1, and it has a mass of 1.67 times 10 to the negative 27th. And protons are located in the nucleus. Neutrons are different than protons only in that they do not have a charge. Their mass is the same, and they are also located in the nucleus. Electrons have a negative charge, and what I really want you to know, you don't have to memorize these numbers here, but what I really want you to understand is the mass of protons and neutrons compared to an electron is off by a magnitude of about almost 4 zeros. So that's almost a thousandths. If you take a proton and divide it up into 1,000 equal pieces, that's roughly the mass of an electron. Roughly, I mean that's 9, so but not quite, almost 1,000. So, but you know, what was I say? So these guys are much smaller. So when we talk about the mass of atoms and the mass of molecules and stuff like that, when we're calculating that, we usually just negate the electron because they're so small. You'd have to go out to a lot of significant figures to make this value of importance, the mass of the electrons. And electrons are not found in the nucleus, but they are found moving around the nucleus. So they're on the outside and they're moving around. They're not stationary. So for helium, the helium atom, 2 atoms, 2 protons, I'm sorry, helium atom is made up of, this example of helium is made up of 2 protons, 2 neutrons, and 2 electrons. It will always have 2 protons and 2 electrons. Helium atoms may have a different amount of neutrons once in a while. But the point I want to bring up here is that if you have 2 protons and they're each positively 1 charged, then overall the helium protons are giving a +2 charge. The 2 neutrons, or more or less neutrons, wouldn't change the charge at all because neutrons do not carry a charge, they're neutral. The charge of 2 electrons would be -2. So the overall charge of helium would be the sum of all these, so it would be +2, +0, plus -2, which would add up to 0. Please note that atoms have no overall charge. Atoms do not have a charge. Atoms have no overall charge. Things do have charges, but if they do, they're not atoms. They're called ions. So atoms always have the same amount of protons as electrons. All atoms have the same protons and electrons. This is going to be important for what I'm going to talk to you guys about on the next lesson. So let's just do another example. We did helium. Let's do neon. So neon atom has 10 protons, it's got 10 neutrons, and it's got 10 electrons. If we sum these guys up, the total, it should always add up to 0 because all atoms have a charge of 0. So the charge of 10 protons would be +10, the charge of 10 neutrons would not have a charge, and the charge of 10 electrons would be -10. So the overall charge is 0. So that's just the pattern that we would use. Again, you can have a different amount of neutrons. It doesn't have to be perfectly 10s. There could have been 9 neutrons or there could have been 11 neutrons. So the number of neutrons does not change the charge of it.
The difference in number of neutrons of an element we call an isotope. If we have, let's say this neon with 10, and we have another one with 9 neutrons, those would be isotopes of each other. If you have a different amount of protons, it becomes a different element. The number of protons determines what the element is, and if we didn't have an equal amount of electrons, then we make that an ion. All right, the last thing is a handout. In class, I'm handing out this handout, but on the website, I will have a link to this. And the handout is just a little bit on how do we know that there's atoms, more sophisticated technology today, and how we can actually see atoms. Make sure you read this, answer the questions on there, and the review the vocabulary in there, the terms in there, because there will be a question or two on the test based on this reading of seeing atoms, the STM. Make sure you read over that and answer the 3 questions. So that'll be linked on there. So I know there's a lot of vocabulary and kind of history involved in this one, so there is no practice shop to just work on. You got to study these notes. I highly recommend you make flashcards and start studying about these scientists and these breakthroughs and what they did earlier than later, because a lot of times people say, like, yeah, I know this, but then when it comes to the test, they just blank out and forget. If you practice, you'll become a good test taker. People that say they're not good test takers aren't practicing enough, and they're not practicing maybe enough or practicing wisely. A wise thing to do, make some flashcards based on what we just talked about here. If I can help you in any way, shape, or form, please come ask. That's what I'm here for. Take care and happy Halloween.